Hello. All right, so today we're going to take a look at our first lesson in Unit 3. We're going to take a look at Newtonian gravitation. And this is a wonderful topic. So you've obviously been using gravity all throughout this course. And you have been using 9.81 meters per second as the acceleration due to Earth's gravity. And that works well if you were talking about the relationship between objects and the Earth, if the objects are relatively light, much lighter than the Earth, and if they are roughly on the Earth's surface. And it breaks apart anything outside of that. So today we're going to look at a more general way of looking at gravity. So early in the formation of our galaxy, tiny gravitational effects between particles began to draw matter together into denser configurations. So the whole idea of gravity is that there's a force of attraction between any two things that have mass. If you study relativity later on, we will learn what our current understanding of the reason for this is. That the gravitational force of attraction between masses is a function of the effect of mass on the bending of space-time, actually. You don't have to worry about that for this course. We're just going to look at the effect, not the cause. But the effect is this. When any two objects are considered as a system, there exists some force of attraction between them. And in the early universe, the force of attraction between these particles is enough that we get a lot of small individual particles feeling forces of attraction towards each other and condensing into clouds of particles and eventually into larger masses, forming structures. So eventually we get the Milky Way galaxy, we get individual stars. Eventually those gravitational forces will cause stars to collapse, but that can result in supernovas, which spread that material out. And gravity has moved material all throughout the universe. In fact, this process of gravitational attraction accounts for the overall structure of the entire universe, despite the fact that it is the weakest of the four fundamental forces. And in grade 11, you should have learned about the four fundamental forces. Gravity, the strong nuclear force, the weak nuclear force, and the electromagnetic force. But we'll get to that. Actually, we'll get to it right now. So if you recall, there's the gravitational force, the electromagnetic force, the weak interaction, and the strong interaction. Gravity is obviously attraction between masses. Electromagnetic force exists between particles that have charge. And then the weak force is responsible for nuclear decay, and the strong force is responsible for holding the nucleus together. But of those, this is actually the weakest of the four forces. And yet without it, we don't have the universe as we understand it. So this is what we're going to look at today. How does the gravitational force work? So gravity accounts for how the planets in our solar system move and orbit the sun. And Newton, whose laws of motion provide the foundation for our study in mechanics, used known data about the solar system to describe the system of physical laws that govern the movement of celestial bodies around the sun. In other words, people had already done research to look at how the planets moved around the sun. People like Kepler and Copernicus had done the math necessary to know the orbital periods of different objects, and from this, Newton is able to piggyback on their work and develop the universal law of gravitation. And that's what we're going to look at now, the universal law of gravitation. And it basically states this. There is a gravitational attraction between any two objects. with mass. And then we can say, if their masses, and we're just going to define some variables here. We're just going to say our M1 and M2, and the distance between them are and I'm going to color code these. So we have mass 1, mass 2, and R. Well, we can work this out. There's a mathematical relationship. So don't write this till I'm done writing it, because I'm going to kind of substitute a few things in as we go. We can say the force due to gravity. And first, let's just talk about proportionality. How does it go on proportion? Which of these is going to make gravity's force bigger and which smaller? I like to think of it that way. So if we put a fraction line here, again, don't draw this yet, anything on the top will make gravity bigger. Right? If we put the number 4 and the number 8 on the top of a fraction, 4 times 8 is 32, that's going to make a bigger number. On the other hand, anything we put on the bottom of the fraction will make the force smaller. So the question then becomes, where do the mass of the objects and the distance between them fit in? And it should be pretty obvious. If an object is heavier, what do you think that will do to its effect on gravity? Well, hopefully you're saying that it will make the force of gravity larger, and that's true. So the mass of the two objects goes on the top of the fraction. Heavier objects exert a larger force due to gravity. And lighter objects will exert a lighter force due to gravity. Keep in mind that it's the mass of both objects doing this. You are not especially heavy. You're certainly not very heavy at all by galactic standards. But you have a large force of gravity sitting here on Earth because the Earth's gravity is large. If you weighed as much as the Earth weighs, the force of gravity between you and the Earth would be much, much bigger. Almost double what it is now. On the other hand, radius, distance between them. Well, we know that the further away you get from something, the less you feel its gravitational force, right? As we move away from Earth, we are less pulled by its force. This is why, even though Jupiter is much bigger than Earth, we are being pulled towards the Earth at all times, not pulled towards Jupiter. So the distance between objects goes at the bottom, and Newton discovers through his studies that in fact it's not proportional to the distance, but to the distance squared. This is what we call an inverse squared relationship. We'll talk more about that in a minute. And then, in math, you should learn that if you have a proportionality, then you just need to figure out that slope. What is the rate at which this is proportional? And if you do that, you can take a proportionality and turn it into an equation. So Newton does this, and we get the gravitational constant. The gravitational constant. And I think I typed this below, but I think it's always good to handwrite certain things anyway. So we're going to handwrite that. And actually, I should color code these others, I guess, since we're here. G is the gravitational constant. And the gravitational constant was solved for simply by setting up these proportions and then solving. We can talk about, it's not quite that simple in practice, but there we go. And the gravitational constant is a wonderful number. It's 6.67 times 10 to the negative 11. Ready for this unit? Newton meters squared per kilogram squared. Oh man, Newton meters squared per kilogram squared. That may seem crazy, but really, if you think about this unit and you plug it in here, when you plug this unit into this equation, the mass is in kilograms and mass is in kilograms. So those two masses will cancel those 2 kilograms. The distance between them is in meters, and it's squared, so that'll cancel that meters squared, and you'll be left with newtons. So really what the gravitational constant says is that for every system where the total mass of the objects is 1 kilogram, that happen to be 1 meter apart, you will experience 6.67 times 10 to the negative 11 newtons of force as a result of gravity. That's the gravitational constant. It tells you how much gravity there is on the basis of how much mass is in the system and the distance between the masses in the system. Note that the mass doesn't have to be equally distributed. You get the same amount of gravity from this as you do from this. If this is 50 kilograms and that's 50 kilograms, but that's 99.99 kilograms, and that's 0.01 kilograms. The force of gravity between these objects, sorry, I should have scrolled over. If you look at these systems, the force of gravity between them is the same. Gravity depends on the total mass in the system, not any one individual mass. As long as we were to say the distance between them is the same, if that was 100 kilometers, and that was also 100 kilometers. So again, the gravitational constant may look intimidating at first, but really it's not intimidating at all. All it tells us is that if we take a system that has a kilogram of mass and a meter between the two masses, you'll experience 6.67 times 10 to the negative 11 newtons of force. That, by the way, not a lot of force, but if you think of the implications of this equation, it means that as the distance between them gets smaller and smaller and smaller, the force will get bigger, and as the masses get bigger, the force will get bigger. Those are the two ways to increase gravity, to either increase the mass of the system or decrease the distance between the masses in the system. All right. The gravitational force is always attractive. Every mass attracts every other mass. Therefore, the direction of the force of gravity on one mass due to a second mass points from the center of mass 1 towards the center of mass 2, and vice versa. All right? So the force is always attractive. The force always points in the direction of the other mass. And this means exactly what you would expect it to mean. It means that whatever the force in one direction is, the other one will just be the negative of that. All right? The second force due to gravity is equal but opposite to the first. All right. Now, I just point out here again that it's an inverse square relationship. An inverse square relationship, and just a reminder that that means that this force isn't constant just based on the mass, but decreases as a function of distance. So the accepted value of gravity on Earth is 9.81 meters per second. This value decreases with the increasing height above the Earth's surface. You could work back from this to find the radius of the surface of the Earth if you wanted to. if you wanted to. I will leave that. I will commend that to your work. But what we will do is take a look at a couple examples. So keep in mind that in all of these examples, we are going to be using the universal gravitational equation, which is that the force due to gravity is the gravitational constant times, excuse me, the product of the masses of the two objects divided by the distance between them squared. All right, that equation is our North Star when we do these. I am very sorry that you all just had to hear me sneeze in here. I am still having some pretty serious seasonal allergies, but that doesn't excuse sneezing next to a microphone, so I'm very sorry about that. All right, so I'm going to stop this video now, and then I will actually put a video below example 1 showing just that, so you can kind of watch this in pieces. All right.